Hello and welcome to the third of my videos aimed at students who are considering taking A-level maths starting in September. Okay, this third video is going to be about calculus in general, but mainly about differentiation. Okay, so that's my last video. Differentiation is about finding the rate at which something changes. Integration is differentiation backwards and has other applications to do with finding areas, but for this video we're mainly thinking about differentiation and rates of change. Now, this is a familiar graph to you. This is the y equals x squared graph, and the rate at which this graph sort of gets steeper, which we know is a gradient from GCSE maths, is, well, it's changing, isn't it? At the bottom it's flat, at the top it's getting steeper and steeper. So anywhere on that line, if we want to find the gradient, we can't rely on just what we did at GCSE. We've got to do something else. Okay, what I've done here to get the gradient at a particular point is to draw a tangent to the curve at that point. And I've just chosen a general point x. Well, x squared, because we know that y is x squared. And we're going to try and work out the gradient of that line. Now, there are rules. All the results that come out of differentiation are things that you will probably need to learn. What I'm doing here now, what I'm about to do now, is trying to show that the result works from what we call from first principles. But generally, you're going to just know these results. And there'll be a list of ones that you can learn, which I'll give a few more of towards the end of the video. For going back to what we're doing here, go and remind ourselves what we did when we found the gradient of the line here. We found 2 points, generally a long way apart. I've not put them a long way apart. I've taken the two axes intercepts here. But generally speaking, you take them a long way apart. And then you apply the rule, difference in y over difference in x. Well, in this case, that's 3 take away 0 over 0 take away minus 2, which is 3 over 2. So the gradient of this line is 3 over 2. And it's 3 over 2 across the whole line, because it's a straight line, it's going up at a constant rate. So in this case, it's not going to be a constant everywhere, but we can still work out a formula for it. So, rather than what I did in the last case, where I tried to look at points a long way apart, here we're going to look at points very close together, so they're still kind of at the point where the tangent is along the line of y equals x squared. So we have this thing, what we call delta x. Now, delta in this case is a Greek letter, but delta x means a very small change in x. Well, it means a small change in x, but a change in x. But in this case, it means a very small change in x. So we're going to find out what the gradient is between 2 points, that point and the point that's so a little way up the line, by delta x. Okay, so this is where we get to do some exciting algebra. I'm using function notation here, and I'm saying that it's still the change in y over the change in x. Now the change in x is delta x. It's because we're finding the gradient between the point x equals delta x and x. So those two cancel out. So the change in y is this small change which is delta x. Now, what's the change in the y value, or the function value? It's the function of x plus delta x. Take away the value of the function at x. That's just, we're just reading off the two. We're reading off what this curve is at x plus delta x, and there, that's x. So when we come back to here again, we're going to, I'm going to do it down here, continue down here. So that is x plus delta x all squared, because that's, I'm just taking the function of what's in the brackets, and what's in the brackets is x plus delta x. So I'm squaring that because that is the rule for this function. Taking away f of x, which is just our x squared, all over delta x, which we're going to get used to writing. So now let's expand those brackets. So we end up with x squared plus 2 times x times delta x. That's just the expansion of something plus something else squared. We end up with 2 of them. And then plus delta x all squared. Take away x squared. All over delta x. So what can we do with this then? Well, x squared, take away x squared, well, that's just going to disappear. Okay, so now we've got 2x delta x plus delta x squared. So I'm going to kind of do a little partial fraction type thing, but it's not, there's only one thing on the bottom, so it's sort of too difficult. 2x delta x over delta x plus delta x squared over delta x. Well, that can cancel with that, and we're left with 2x, and that can cancel with that. So what we're left with is, I'll be printing this off so I can move it up a little bit. What we're left with here is 2x plus delta x. Now this is where I'm going to introduce some more notation. I should have done this all the way along actually, because what we're trying to find out is, we've got this delta x thing, which is a little bit artificial. We're trying to make that as small as possible, because we're trying to find the gradient not between x and delta x, but you know, when delta x is so, it's vanishingly small. So this is a notation which I could have been writing all the way through, but I'm only want to introduce it now. We're saying the limit of this thing as delta x tends to 0. And that is notation that you will get used to seeing. So the limit of this thing as delta x tends to 0. And well, I can rewrite that limit notation across all my working out, but I'm just going to do it at the bottom here. Limit as delta x gets closer to 0 of this thing. Well, basically what we're saying here is that the delta x thing, we couldn't really do it when we still had delta x at the bottom, because 0 getting smaller and smaller and smaller, and the whole thing gets out of control. But once we've cancelled things out, we can actually see that delta x is just going to get vanishingly small, and what we're left with is 2x. And that says that at any point on the line y equals x squared, if you were to take the gradient of the line at that point, it would be 2x. So, just to take a point on this graph, 3, 9, which is about there, the point of the line is obviously 3, 9, and the gradient is 6 at that point, is 2 times the value of x at that point. Now that is just the rule for differentiating the line y equals x squared, and that is going to become second nature to you. You're just going to remember that. I'm going to show you some more notation in a minute. Right, let's go on to that page now. Here it is. There's various notations. Now, there's 2 different notations for differentiation. This is because 2 different mathematicians, one of whom the very famous Isaac Newton, and the other one, a German called Gottfried Leibniz, they worked on this together. Well, they didn't work on it together. They worked at it at the same time, and then a massive falling out, inspired mostly by the fairly obnoxious Isaac Newton, actually. So they both have different notation. I honestly can't remember. I can never remember which is which. I think this is Leibniz's notation, and that's Newton's notation. But if anybody's watching this who knows I'm wrong, then sorry, don't take that as regret. But basically, if you write in function notation, here's the one we've already done. F of x equals x squared. So we say f dash of x equals 2x. That's the one we've just shown. Okay, and all the other curves that you may be familiar with, you went through in more advanced GCSE, they've all got their own, they've all got the rules. Now, I could demonstrate using the delta x method, the cos x sine x, but I'd be using bits of math that come a bit later on with cosines and cosines in the course. So you need just remember these for now. Cos, if you remember the cos x curve, let's do it with a straight line. If you remember the cos x curve, that starts that starts up here and immediately starts going. Oh, hang on, still got a straight line on. Immediately starts going down. The sine curve starts going up. That's because to start with, the cosine gradient is actually negative. It is actually negative sine x, whereas the sine curve is going up, and x, and actually f of x, f dash of x is actually cosine of x. That's just, I'm telling you that now. It's a result you'll see much later on in the course, and you'll be using the relationship between cosine and sine and their curves as you go on through A-level maths. The other notation here is the dx notation, which is particularly useful when you're solving things called integral equations, which are much later on in the course, in the A-level course. But dx by d equals 2x plus 1. And I'm not going to try and justify that at the moment, other than that is actually the correct gradient of the curve y equals x squared plus x is 2x plus 1 at any point. So that's basically it. That was basically a quick introduction to differentiation. So to summarize, when you differentiate a curve, you're finding the function of the gradient at any given point. And there's lots of results that you'll learn, like the ones I put up on this screen, but you can also demonstrate them I mean, you can try doing that for x cubed. I'll just tell you the result for x cubed. D by dx of x cubed equals 3x squared. If you're really feeling ambitious, draw yourself a grid and see if you can actually prove that using the delta method. That may not be something you want to do straight away. Okay, so thank you very much for watching this video. I'll probably make a couple more about subjects on the GCSE course, the A-level course. I've just not decided which one to go back to my books and see what other things I can make quick videos on. But I hope if I don't make any more, you've got a flavour of some of the things we'll be doing in the first term on an A-level maths course. Thank you very much for watching.